Okay, the last talk for today is by Bob Jenkins, also from the University of Central Florida, talking about realization of the equilibrium of soliton gas via primitive converge.
All right, Peter, thank you to the organizers for inviting me to come back and give a talk on. I chose this topic because the first part of this talk is going to be some things I think I reported on 2 years ago that and so energized by all the talks that went back to the Muller Institute, and big chunk of this was just done there. And then we went away and got busy, and now it's almost ready to be published. So I figured I'd talk about that. It's joint work with Tim McLaughlin, Manuela Girotti, and Tamara Grava, and Alexander. All right, so I'm going to try and get you to the wine and dinner on time. So I have the advantage of everybody talking about this before, so I get to skip many things, so I'll go quickly. So the object of my study is going to be modified KDV. Okay, so it has the lattice structure. Don't need to say much of this stuff. I'm a Riemann-Hilbert guy, so I tend to like this. If you don't like Riemann-Hilbert, that's I completely understand. But I want to just say some things, okay? So you have some reflection coefficient on the real line. This is for vanishing data. And then you have holes in your problem. These are encoding the solitons. So you have your residue coefficients. These things are telling you the initial position and the initial phase of your solitons. And the actual eigenvalues, right, they're telling you the speed and the amplitude of solitons. It's all encoded that way. Okay, so you solve this big analytic function theory problem and take some limits, and I'll pop the solution of MK. Okay, so we've got our one soliton solution. This is what I said. You want to take n soliton solution, you can turn it into a linear algebra problem, or it has this nice Fredholm determinant representation. This is nice if you want to take the limit as n goes to infinity. Making some assumptions on the way that these Norman constants are chosen, of course. Okay. And so you can try and analyze this. And so, okay, this is something everybody has said already, right? That interactions occur pairwise. And then if you want to figure out the shift due to many soliton interactions, you just add up those shifts. And okay, this is the picture we've seen many times from Allen companies. So this is KDV, but you take a big soliton, fire it into the gas, and it gets, if you look at this term, the tall soliton gets advanced, accelerated by each of the little bumps, and so it's further ahead than it should be. This is an MKDV picture. I think Ken showed this a few days ago, where we started a big soliton in a vacuum, run it into the gas, and then you can see it sort of bends forward from where it would be. The green line is where it would be if it were all on its own. All right, so there's different ways to model soliton gases. And if you want to look at realization, so not average quantities, but like this is a limit of some solitons and pass to a limit. Zakharov and his collaborators proposed this model from sort of a formal argument, and it doesn't look anything like solitons anymore. Okay, so we have now bands in the complex plane. You want to think that your eigenvalues live here. This is MKDV, so it has a quartet symmetry. So for simplicity, it makes the problem much easier to consider the problem where you only have imaginary eigenvalues. But in principle, you could have symmetric quartet spines or something out there, but then it would behave much more like NLS, much richer thing, something to do in the future. Okay, but now we have two fields, R1 and R2, and you want to sort of think of these things as something like some smoothed out version of your Norman constants. Okay, and I'll say a bit more about that in a second. Okay, but forget soliton gas. If you just say, stick this problem in here, glue in this phase function, you can solve it. You can show that whatever comes out solves the MKDV equation. Okay. Yeah.
If you choose your discrete eigenvalues on the imaginary axis, they're all stationary, right?
No. For MKDV, these are in this situation it behaves very like KDV. When you put them, the constant speed lines for MKDV are hyperbola. And so like for instance, the zero speed line is like across to the origin. So a bound state would be like if you stuck them on a quartet like that. Yeah,
You have no constraints on functions R and R2, for this to be.
yes, I do. If this is real MKDV, then these need to be real functions. And also clearly, if R1, R2 is 0, I run into some big problems, right? But for what I'm gonna say, the functions R1 and R2, you should think of them as maybe smooth functions. One derivative is enough to make things work. And they can, I don't want them to change. So I'm gonna do the case with 2 bands, but you get many bands. They can change signs on the different bands, but not inside a band. So on each band, it's a positive or a negative function independently, and their product can never hit -1. Other than that, really general. Okay, and even later, I'm gonna show some formulas. You can even have a reflection coefficient here if you want. Okay. All right, so how do you get this from solitons? Okay, so back to the soliton picture. I'm gonna let eigenvalues fill out these 2 bands. And I'm gonna have these Norman constants, or let me call them residue coefficients. I don't want to call them Norman constants for a very specific reason. I pick the residue coefficients, and now I want to pass to some limit. Okay, so how does this work? So Ken talked about this a couple of days ago, so I'm gonna try and do this fast because I want to do the other case. Okay, so there's a trick. You just you take the meromorphic problem that has its poles, and you make this formula. You put a little disk around each pole. You make this transformation, and the new function is piecewise analytic. H is homomorphic. Reason for the name. Okay, but you pay a price. You pick up a jump on the circle. So that's okay. 2 poles. As long as they all have the same triangularity, though, you're just going to remove them all at once. And the magic of well, it's not really magic, right? It's just commuting matrices. This thing now removes all the poles at once. And if this starts to smell a little bit like a Riemann sum, if you choose these Norman constants, right? I always call it Norman constants. If I pick these residues to be some smooth function times 1/n sampled at the eigenvalues, positions of the eigenvalues, and I assume that the eigenvalues are sampled from some density function on the spike, then this thing will converge to an integral. So you take the limit out on this disk where everything is controlled because now the denominators are bounded. Take the limit out there, now you have integrals. That's just a Cauchy transform. You collapse it back onto the band and you get this. So this is the Zakharov primitive potential where R2 is 0. So it gives you a triangular picture. Okay. So, okay, we're halfway there. We can get one of these potentials, but only with one field right now. Right? Now, one thing I just wanted to mention, this, where did it go? Here. This choice to sample the residues like 1/n times some function. If you go back to what it means for a 1 soliton, that means that we're putting the centers of the solitons out at like log -n. So we're pushing the solitons off to -infinity. Or actually, in a second, I'm going to switch some signs and send them to +infinity, but that's just normalization stuff. Okay, but it means you're putting all of your solitons off at infinity. Now, this is a little bit of a lie because that's where one soliton sits if it's by itself. You're cramming them all in there; they repel each other. So you have to take this with a bit of a grain of salt. Okay, pass to this limit, and now you want to analyze this problem. Like this. Maybe it's a soliton gas, maybe it's just a fun exercise. What's the solution of MKDV look like? Okay. So this was work with, yeah.
So the expression for R1, you have F, which would be equivalent to function.
Yeah, so
and
F
the row is.
the density of eigenvalues. Right. So that product is now R1. Okay, so I renormalize things so that the gas is on the right, so it's right to the left. But this is work with Ken and Tamara and Manuela, for you take this thing and then you analyze the long time behavior. So let T go to infinity and see what happens. Okay, and what you find is that in this situation, all the solitons are put at +infinity. So it's not really a surprise that when you look at the asymptotics for large negative x, you get 0. And in the large positive direction, you have just sort of an elliptic wave, right, where all the parameters are constant. But then there's this modulation region in the middle, and you have the modulation is exactly described by the Whittam evolution. There's the picture similar to what Alex showed in his talk, okay? And it's just exactly what a modulation that describes how that connection occurs, okay? You can see that in this case, how do I organize these things? This V2, that's the bottom of the spectrum. So it starts to modulate when you go into the frame of reference of the slowest possible soliton on your band. And it modulates up to some number V3. That's not this, it would be great if it was the speed of the fastest soliton in your band, but it's a little bit. Okay. But you can exactly compute on these things. Okay. So you have this expression and you also have a phase shift, and this thing you can exactly compute. I don't think I put it in the slide, it's an oblique formula. I'll show you a nicer one in a bit. Okay. Oh, actually I did. It is. It's not that bad actually. But it's log transform of the R1, the norming constants, and then this thing is related to the fact that you're in an elliptic background. So ds over this is just like the polymorphic differential on your. Okay, so I'm going to skip this slide. This is just about this. So this is a little bit later with Denise was talking about earlier. So all the Riemann-Hilbert analysis is just driven by, you need to understand the sign of this space function. There should be a t there, not a 0. But so basically what's going on, when you're at slow velocities, the entire band is decaying. So you can just replace this with 0, you get nothing. And as you evolve, the zero growth curve hits the bottom of the band. And as soon as that happens and it starts to move past, then you have to modulate something and you have to have okay, if you're into the Riemann-Hilbert stuff, you have a little g function that grows and is supported on this growing band until it hits the top of the spectrum, and then it detaches, and that's now it's on a fixed band, and that's why you don't have a modulated wave anymore. It's just the constant. All right. So that's the g function thing, and then one of the things we were able to show in this work was that. This is related to things Alex was talking about. The g function is sort of the object that ends up solving the NDR equations or its derivatives. Okay, so the g function is a combination. You can't see it really here. Maybe it's better on this slide. Okay, it's sort of coded in here. It's t times basically the quasi energy and x times the quasi momentum. The derivative of it is, and you look at these quantities. And this is a condensate setting, but it satisfies the NDR equations exactly for MKDV. That would have 4k squared here. I think it was MZ squared for NLS, or MZ maybe. But these are the NDR equations for MKDV in the condensate setting. So when we do these primitive potentials, it's always a condensate. We haven't been able to avoid that. So you could get the equation of state for the velocity as well. And you show all these things are satisfied by the gas. Okay. All right. So in a little bit of time I have left, I want to tell you how you get the full primitive potential. This is the more recent interesting one. Okay. So what you have to do is you have to go back to the n-soliton problem again, always back here, but you have to modify the way it's stated. Okay. So I think most people are familiar with sort of having one flavor of soliton, so that all of them have one triangularity. But this is actually a choice when you build your inverse scattering theory. You can, so if you know this, if you don't, if none of these words make sense, just tune out for half a second. You can take the A function, the transmission coefficient basically, and factor it, and split it into 2. And instead of putting it all in the first column of your matrix, you put some in the first column and some in the second column. And the effect is it changes the triangularity of some of your solitons. Okay.
So like physically it doesn't change the soliton itself, like how does it change?
It's no, the solitons are the solitons. It's just the way you encode them into the problem.
So it's like you use half of the solitons to do the R1 and half is the
Yeah, so what really, so here's another way to think about it, okay? You have these residue coefficients, and there's a general idea that if you have really large coefficients, you don't like that. There's a way you multiply by a Blaschke factor and you change the triangularity, and when that happens, you take the reciprocal of the coefficient effectively, times some Blaschke factor stuff. Okay, but that means if you have a very large coefficient here, this one will be small. So if you're thinking, I want to have this 1/n behavior because I'm going to spend all my solitons off in minus infinity, then if I have in this picture, if I had coefficients were linear in n, it would be sending them to plus infinity. But I don't want to analyze a problem with big coefficients, so I renormalize it. So in this picture, they're both small. That's sort of the
Or some use center plus and some maximum.
yeah. So at the physical, there's nothing different. I haven't changed the problem, it's how you encode coefficients here. If you think in terms, so this is why I was trying to be careful, even though I can't do it. There's the norming constants and there's the residue coefficients. The norming constants are, if you take the two Yost functions, it's the thing that relates them, that's the physical object, right? That doesn't change here. This number is the norming constant divided by the times the translation coefficient, basically the residue. Right, and so if you do this, I think one of them has the reciprocal of the norming constant and the other one has the norming constant.
Simply 0%.
Yeah, all simply 0. All right, so for simplicity, I don't think this is the way we've done this right now, but I think this can be relaxed. I'm going to assume that I have an equal number of sort of up and down solitons and that they alternate and that they're equally spaced. These things can be relaxed, but you have to work harder. Okay. So now I need to remove the poles, but this is a more complicated procedure because, okay, so what am I going to do? Well, I'm going to take my matrix, which has poles, and I'm going to multiply it by some lower triangular thing, and that's to kill all the poles, that the lower triangular ones that have the C's. So this factor B, it's now a Blaschke factor, it's got a pole everywhere the other one has a pole. But what that's doing is it's adding the second column to the first column, and the second column has poles at the zetas, so I didn't need this to vanish everywhere with the zetas. So you need this sort of factor so that you're not putting bad things in. Okay. And then this function C, I'm just going to pick it so that it matches, so that all the residues work. It's something we'll just choose later. So that's going to remove the lower triangular poles. And then I have this factor, I'll then multiply by this and try and remove the upper triangular ones. Okay, so that's the game. We'll do that on some disk. Okay, and then this equal spacing trick, this Blaschke factor can be expressed in terms of gamma functions because of the equal spacing. And then on the circle, you can rescale everything and use Stirling asymptotics, and this thing converges just to this ratio of square roots. Really nice. In general, this would be some log transform of the densities of eigenvalues for the sets, and so you'd have to work that order. But really, the only thing we really need to make this argument work is that this function converges to something which is analytic, except for on this jump, and that it has some jump across it. So that's why I'm very confident you can make this work in the other situation. Okay, so you pass to the limit on the disk. Now these jumps, these functions, we're going to assume that these functions C and D are analytic inside the loops. You could probably get away with assuming that they're just continuous and having a D-bar problem, but it's a more complicated picture then. Okay, when you collapse everything back onto these bands, now you have some jump that looks like this. Okay, so here's where this is the jump relation of the limit is showing up. Okay, and now you can take different perspectives now. If I want to just arrive at Zakharov's primitive potential, I'd choose C and D like this. You choose this to be C, this to be D, then you at the Zakharov primitive potential. Or you can say C and D are the things that are forced on me because I know those things. I measured the solitons at the beginning, and then R1 and R2 are given by this. It's just a matter of putting a big pattern. Okay. All right. So we've arrived at the problem. And if I want to finish on time, I've got like 2 minutes to go. But we'll get in touch. Okay. But now you wanna do this analysis like we did before, but there's a funny thing about this problem that seems really scary at first, but it actually makes it much easier. We were worried about where the sign of this was positive and where it was negative before. But now I've got both the exponential and its reciprocal in the problem on all the jumps. So what that means is it's always bad. There's always a big jump. But that's actually a good thing. It means that when you build this G function that has to control things, it's not modulating. It's got to be supported on the whole band always because you have to control everything. So you build a G function that has no modulation, it's just fixed. So it's exactly the same construction as before, except for it's only determined by the endpoints of your spectrum. You build the thing, and then what happens is, if you like the Whittam theory picture, right? This thing, the combination of the quasi-energy and the quasi-momentum with x and t. When you do the Whittam modulation theory, what happens is one of the zeros has to stick to an endpoint when you get the simple waves. But now they're free, they just move. And so as you evolve time, you've got a couple of stationary points on the real line. This is important when you have reflection. This is when you're going to see radiation in this sort of regime. When they peel away from the real line, you don't see any radiation anymore. You're sort of outside that regime. But then the zero just moves through the band. And as it moves through the band, you have to change things up a little bit. I'm not going to get into the Riemann-Hilbert of that. That's gross. At the physical level, what it does is it's responsible for modulation of the phase. Okay, so your solution is just a elliptic wave solution. Okay, but and it's all the parameters are fixed. But if you go to plus or minus infinity, if you send t to plus or minus infinity, you have these phase shifts. Okay, and this term, you can explicitly compute these, x0 plus, x0 minus, and those will care about as you pass through this band. So I didn't write down those formulas because it has many pieces. But if you compute the total phase shift, it's the integral of this expression over the band. And if you want to be ambitious and put a reflection coefficient on the real line, there's also some phase shift to the reflection. I didn't put that in just to avoid the complication of it, but that's what it is. Okay. And so here's a movie. You turn this thing on. This is for almost a monochromatic gas, so all the eigenvalues are sampled like this. And what's happening is there's an expanding region where this modulation is occurring, where these things are changing. And then on the left and the right, it's just a standing elliptic wave. You can do it for a more full band picture, and it's less pronounced what's going on here. But this is a lot more close to the elliptic equilibrium gas, because you're not seeing this modulation from a gas to a zero state. All right, so that's it. The things we're working on now is to make this picture work for a higher genus, so put many, many bands into the problem. We sort of know what happens if it's always the full gas picture. So if you both always have R1 and R2, then basically this picture happens here, except for now you have many bands, and you just see modulations every time the free zero passes through there. Okay. What's much more interesting is when you would have combinations of sort of full bands and half bands, because then you would have some modulation and some sticking, and you can see more interesting dynamics, I think. Let me just go back here for 1 second, only saying the thing. So I at first thought of these particular this. So I originally thought this problem was really weird, but now I really like it. If you stare at this for half a second, if you let R1 and R2 be reciprocals of each other, so R2 is just 1 over R1, then this is exactly a finite gap potential. So what you should really think about these primitive potentials as is a generalization of the class of finite gap potentials, where you can connect any finite gap potential on one infinity to the other. And if you do asymptotics of these things for large x, fixed t, let x go to plus infinity or minus infinity, you can show exactly that. That if you just count the number of bands where, let's say, R1 is non-zero, that'll tell you the genus of one infinity, and the number of bands where R2 is non-zero will tell you the genus of the other. So it's a very cool generalization that I think we can do a lot of work with. Thank you.
One important thing is that you put some randomness on the normal constants sampling, but the limit is kind of almost surely goes to the distribution. So the U of xt has an almost sure limit, it's not non-homogeneity.
So I should say right now, there's no randomness in this picture, right?
You were saying we sample some of data becomes an integral. We sample.
So you might be able to do that. Well, at this point, I just mean you fix a density and then quantize eigenvalues as n goes to infinity. So there's no randomness really. But I mean, I think there are ways to put randomness in this. I just don't know which ways are the best.
So if you want to have a non-common, say, I guess you have to have some randomness, and then in this case, U will not be like a fixed solution, right? And you will not, its average will not satisfy the equation.
Yeah.
So
Okay. So the other thing is, this convergence is on compact sets. You can work harder and push it to x and t being a small constant times logarithm n.
yes.
If you look at x and t like bounded constant times logarithm n, you might expect this is sort of the edge of the condensate where some of your solitons are actually now traveling fast and escaping the colloidal wave, right? And so this should be sort of like the dilution. And so maybe in that, this is all just hand waving, not so.
Yeah. No.
But that sort of that scale, we expect that maybe we can see non-condensate K.
Yeah.
But still, that's still a deterministic picture. That's you could put random.
But I thought you were putting some randomness in the.
No, not so other people have done that in some situations, but here I'm just doing it deterministic.
It's more discretization.
Yes, it's more like that. I mean, one, a hokey thing you can do after the fact is you have asymptotics for this thing. You could, and these are functions supported on intervals. You could put random Fourier transforms and then ask questions about like random Fourier series with coefficients, and then ask something about asymptotics. But that's not, I don't know if that comes from any physics. It's just yeah.
Other questions for Bob? What about the defocusing case, Bob?
Defocusing.
Yeah.
I didn't get it much. No, I hesitate to say.
Okay. All right, well, let's go ahead and thank all the speakers.